Hey folks, welcome back. In this video we're going to go over question 2 from the 2016 SQA Advanced Higher Physics exam paper. So let's get going. Question 2 part A says an ideal conical pendulum consists of a mass moving with constant speed in a circular path as shown in figure 2A. So there's our mass moving in a circular path and it's moving with angular velocity omega. Part 1 says explain why the mass is accelerating despite moving with constant speed, and it's worth 1 mark. Well, we can say that it is constantly changing direction and therefore velocity, since velocity is a vector, meaning it consists of a magnitude and a direction. So for velocity to be constant, which is the same as a zero acceleration, we would require both the magnitude and the direction to stay the same. However, here the ball is constantly moving in a circular path and changing direction, which means that its velocity must therefore be changing as well, even though it's moving at a constant speed. And remember, acceleration is defined as the rate of change of velocity. So if velocity is changing, then that means there must be a non-zero acceleration. Part 2 says state the direction of this acceleration, and again this is worth 1 mark. Well, remember this is a centripetal acceleration, which means it's going to act towards the centre of the circular path. Part B says swing ball is a garden game in which a ball is attached to a light string connected to a vertical pole as shown in figure 2B. The motion of the ball can be modelled as a conical pendulum. The ball has a mass of 0.059 kilograms. So you can see the swing ball set up here with the ball at this side moving around in this direction, and we've got the radius r of the circular path labelled. B part 1 says the ball is hit such that it moves with constant speed in a horizontal circle of radius 0.48 meters. The ball completes 1.5 revolutions in 2.69 seconds. Part A says show that the angular velocity of the ball is 3.5 radians per second, and there's 2 marks available for this. Well, what we want to do is first find the angular displacement theta and then the angular velocity omega. So to find the angular displacement theta, we can say that's equal to 1.5 revolutions, which we're told up here. And remember, 1 full revolution is the same as 2 pi radians. So we simply just need to take our 1.5 revolutions and multiply it by 2 pi radians to give us 3 pi radians in total. Or you can write that as a decimal if you prefer. We can then use our equation from the relationship sheet omega equals d theta by dt, which relates angular velocity omega and angular displacement theta. However, we don't need to use it in this form. We can actually generalise this to this equation here, omega equals theta over t. So writing down what we know from the question, we're trying to find the angular velocity omega. Our angular displacement theta is 3 pi radians that we just worked out, and our time t is 2.69 seconds that was given in the question. So writing down this generalised equation, we have omega equals theta over t. Substituting in the numbers gives 3 pi divided by 2.69, and putting that into your calculator should give you the answer of 3.5 radians per second, as we were asked to show in the question. Part B says calculate the magnitude of the centripetal force acting on the ball, and this is worth 3 marks. Well, writing down what we know from the question, we're trying to find the centripetal force F. We know the mass of the ball is 0.059 kilograms, we know the radius of the circular path is 0.48 meters, and the angular velocity omega is 3.5 radians per second. So writing down our equation for centripetal force in terms of angular velocity omega, we have F equals mr omega squared. Substituting in the numbers gives 0.059 times 0.48 times 3.5 squared, and putting that into your calculator should give you an answer of 0.35 newtons. Moving on to part C of part B, we have the horizontal component of the tension in the string provides the centripetal force and the vertical component balances the weight of the ball. Calculate the magnitude of the tension in the string, and this is worth 3 marks. Well, to do this we need to consider the force vectors acting on the ball at one point in its motion. So let's just draw the ball first of all, and we can label 2 forces acting on the ball. So it's going to have a weight mg downwards, and it's going to have a centripetal force which we can label F, and let's just assume this is when the ball is at the right hand side of the circular path, and therefore the centripetal force F is going to act directly to the left, horizontally into the middle. And since the vertical forces acting on the ball are balanced, we can redraw this as the mass here, the weight vector mg acting up the way this time, because we're saying the vertical forces are balanced, and therefore we're going to have mg up the way as well. And we could just keep our centripetal force acting to the left just like before. Now the reason we've done this will become apparent in a minute when we calculate the resultant vector. So notice here how the vectors are not joined nose to tail. So in order to calculate a resultant vector, we need to join these 2 vectors nose to tail. So let's start with our mass here, our centripetal force F going to the left, and then let's join the tail of this vertical force to the nose of this horizontal force. So we're just taking this vector and moving it over so that it joins on here, and that would look something like this, and we can label that mg. So we've now got our 2 vectors joined nose to tail, and then we can draw a resultant vector going from the start to the finish point, and let's put a double arrow on that to show it's the resultant vector to make it different from the single vectors. Now this resultant vector represents the tension in the string, so we could label that T. We can then label the right angle to show it's a right angle triangle and put in our angle theta to the vertical, so that's going to be this angle in here. And then to find the magnitude of the tension in the string, we can use Pythagoras. So instead of c squared equals a squared plus b squared, we could write this in terms of the variables we've got. So we could say the hypotenuse t squared is equal to this side mg squared plus f squared. And then we can just sub in our values for those. So we've got 0.059 for the mass times 9.8 for the gravitational field strength on Earth, and that's all squared, plus 0.35 squared, where 0.35 newtons was our centripetal force from earlier. And if you put that into your calculator, you should get 0.457. Now that's a value for t squared, but we want t, remember, so we're going to need to square root both sides. So if you do that, you'll get t is equal to the square root of 0.457, and if you put that into your calculator, you should get an answer of 0.68 newtons. Lastly, B part 2 says the string breaks whilst the ball is at the position shown in figure 2c. On figure 2c, draw the direction of the ball's velocity immediately after the string breaks, and this is worth 1 mark. Well, if the ball is at this position when the string breaks, then we need to draw a straight line tangent to the circle at the point where the ball is. So because the ball's moving in this clockwise direction, we're going to draw a straight line tangent to the circle here, so it should look something like this. So the ball should be going in this direction rather than going back the way in this direction. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.